All right, here we are in our video today. Olbers Paradox. Why the night sky is not bright as day. And some of you are probably saying, well, duh, the sun's not out. That's why the night sky is not as bright as day. Well, actually, there's more to it. Because if you think about what's in our Milky Way, what's in our universe, all those stars out there, in our Milky Way alone, we have 100 billion or more. And there's about 2 trillion galaxies out there. We're looking at about close to 200 sextillion stars out there or more. So let's write that. Let's write that number. Right? 200. That's 200,000. That's 200 million, billion, trillion, quadrillion, quintillion, sextillion. 200 sextillion stars out there. All those stars, all that luminosity should be lighting up the night sky. It should be as bright as day. And so one of the persons that thought about this, that we have recorded thinking about this, was Olber. Heinrich Olber. Let's write his name. Heinrich Olber. And he thought about this in 1823, a long time ago, when James Monroe was the president, way before the Civil War. So all those stars in the night sky, here's the paradox, all those stars in the night sky should light up the night sky, should light it up as bright as day, like I said before. Every patch of sky should show a star. And so many people have wondered about this. Even Edgar Allan Poe talked about it. So where's all the light? How come we don't see it? And it's really a simple explanation in one sense. Let me show you what it should look like if we can see certain light. Now, imagine seeing this in the night sky. This is microwave, and microwave is light. So the electromagnetic spectrum has visible light that we see, and it's the only light we see. But there's other light out there. And if we can see microwave, we would see the night sky like this. So let me get a clean page and we'll explain this. Or we can leave that up there, why not? So the universe has a beginning. We know it has the Big Bang. The Big Bang started this. And we know it has to have a beginning for this theory to work. Because all the photons of light, so some people thought about earlier on that maybe all the photons of light have not reached us yet because the universe is so infinite. But if it has a beginning, then it wouldn't be infinite. The light should reach us. So where is the remnant of the Big Bang? And there you are. You're looking at the remnant of the Big Bang. And the reason why we don't see it is because it's in a cooler microwave length. So on the electromagnetic spectrum, let's clarify that. Maybe it'll be easier to understand. Let's use green. So on the spectrum, the electromagnetic spectrum, we have radio waves. They're the longest wavelengths. And we have microwave. We don't see any of this. If we did, the room would be so bright. We have infrared. Some animals see infrared, like snakes. And we only see visible light. That's all we see. Then there's ultraviolet light, which we don't see. There's X-rays, which we don't see. And gamma. So looking at the lengths, radio is the longest and gamma is the shortest. So we're only seeing visible light. So as the universe expands, it's expanding. The universe is actually expanding faster than light. And you might say, well, nothing goes faster than light. And that's true. Nothing in the universe goes faster than light. But now we're finding that the universe itself, though, can break the rules. So the universe is expanding faster than light. And so to make this easier to understand, the light waves are stretching. The light waves trying to come to Earth are stretching. So they're going from the visible light spectrum that we know. And remember, visible light, let's use red here, put it in there. Visible light, let's see if this comes out. Goes from 330 nanometers to about 700 nanometers. And the longest wavelength of visible light is the red, and the shortest is violet. But if you think about, these are nanometers. Let's fix that nm, nanometers. Let's write it over here. Nanometers. Let's get a clean page, make it easier to understand. Use a black screen, night sky there. So invisible light over here, we have nanometers. That's the wavelength of visible light, from 300 to 700. So that's what we can see. So if you think about microwaves, microwaves are 1 millimeter, up to 1 millimeter. And I'll just write, there's a million nanometers in 1 millimeter. And radio waves are even longer. So we can't see microwave, radio waves, infrared, ultraviolet, X-ray, and gamma. And so again, the universe is expanding faster than light. So the wavelengths are stretching. And what we're seeing, all those stars way out there are now in the category of microwave length. So that's why we don't see them. But the microwave background radiation, let's go back to that picture. Here it is. They're all microwaves and infrared. So the microwave is cool and blue. See all that blue, all that bright light? That's from microwave. We're not seeing this, right? We need some special equipment to see it. So again, a very simple way to say this is that because the universe is expanding faster than light, the light energy, the electromagnetic spectrum, the light is expanding, their wavelengths are expanding, and they're going beyond the visible light range of 300 to 700 nanometers. So when they go beyond that range, as they're stretched out, we don't see them. We need special equipment. And that's why the night sky is not bright. Very simple. By the way, if the universe was static, if it was not moving, then the night sky would be extremely bright. So that's one way we know that the universe is moving, because if it wasn't, we would have a hard time seeing. Or maybe we would have no nighttime. All right, that's our video today.